Hi guys, so I'm going to finish up the last of the concepts that go along with electric field intensity, and this centers on one of the most important experiments in the history of physics, and that's Millikan's oil drop experiment. It was actually done in the early 20th century, so this is probably one of the first experiments that actually take us into the 20th century. I will try to do a simulation, a mathematical lab, where we kind of do some of the analysis that Millikan had to do, but the actual device that does the Millikan oil drop is actually pretty complicated and very expensive. So I'm just going to describe to you what he did and, more importantly, what the outcome was. All right, so let's jump right into it. The outcome, and this is why it was so exciting, was it determined the charge of an electron for the first time. Okay, and therefore allowed the calculation of its mass. In other words, experiments by J.J. Thomson in the end of the 19th century was basically came up with the ratio of the charge to the mass of an electron. He came up with some number. I don't remember off the top of my head, but it was something like 10 to the 11th. So through some experiments with electricity and magnetism, something else we'll show you when we do magnetism, he could come up with this. So we got this ratio, but the race was on to figure out either charge to get mass or to find out the mass independently to get charge. So Millikan did a brilliant experiment where he was able to come up with the elementary charge, and then right away we knew what the mass of an electron was. So that's a pretty big deal. So how did he do it? He used parallel plates and the uniform electric field that comes with it to balance oil drops. Okay, so I'm going to go to the diagram and before I fill in the blanks. So we have two parallel plates. So the top plate is going to be positively charged. You're going to place a voltage across it such that it has positive charge, and therefore by induction the negative plate is automatically going to be negative. In there, he introduces oil drops through an atomizer. So these are microscopic drops. You need a little microscope to see them. And based on the process by which he injects them into that, they become charged. And more specifically, they become negatively charged. Okay, not a lot of charge. That's why he's choosing very tiny drops. But not definitely one or two elementary charge. We're talking thousands maybe, but it was good enough. So the idea is this. We're going to have a balance, a tug of war. Because it's an oil drop, gravity is going to want to pull down on it. But based on the electric field, right? So if I draw electric field lines, the field lines go negative. And since it's a negative charge, the force on that electrically is not going to be down in the direction of the field lines, because that's for positive field charges. It's going to be upwards. And so when you get a drop in your viewer, you basically turn a knob on your voltage such that this drop just hovers in place. And when it hovers in place, and you know its mass, we're not going to talk about how they figure out the mass, but that was fairly complicated. You could balance these two forces, and that's the big physics idea here. Okay, so going to the second bullet is the negative charge drop is balanced against gravity. Okay, so the relevant equation that comes from this is basically Fe equals Fg. It's pretty simple. How do we calculate Fg? Well, either given it or you could do m times g. How do we calculate the electrostatic force on that drop? All right, the temptation is to want to use Coulomb's law, kqqq over r squared, but you can't because that doesn't apply to parallel plates. So we got to remember, Coulomb's law only applies to spherical charge distribution. So we can use the more general equation for electrostatic force, and that's simply taking the field intensity, which can be determined by the voltage across it, multiplied it by the charge of the drop in there. Okay, so that comes from our field intensity equations. So what we can do then is solve for Q. Q is then equal to, and this is the drop now, not the elementary charge, is going to be simply mg all over E. So for example, all right, so if I've got a mass of very high precision shown here and is balanced in a field with 50,000 Newton per Coulomb E field, we can ask what's the charge of the drop. So I can use that equation. You should be able to derive it on your own. This is not something I'd expect you to memorize. Mg all over E. And if you do the numbers, and I have them somewhere here, okay, we get an answer of about 1.9 times 10 to the negative 16th coulombs. So these drops are so tiny they can only hold amount of charge. Now you got to remember, at the time, no one knew what the charge, one elementary charge was. So here's where the brilliance comes in. And this is more subtle, and we're not going to mathematically model it. Is Millikan does this with many thousands of drops. And he finds that each drop has a different charge. But he notices there's a pattern amongst those charges, those drops. Some repeat themselves. You might get something that's the same as this. And then others seem to be incremental. In other words, they only come in certain values. And what he was basically able to do before the age of computers or calculators, okay, so filling this blank, the mathematical analysis based on assumption that charges of the oil drops would come in discrete amounts. Discrete means that it's like an ATM machine. In the ATM machine, you can only take out money that is multiples of $20. So we're assuming that any charge on a drop is due to multiples of the elementary charge. So you're not going to see a continuous range of drops, but they're going to come in tiny discrete amounts that had a greatest common denominator. I don't know if I want to say that. I want the least common multiple, greatest common multiple maybe is what I want to say. It's been a while since I've done that. Greatest common factor. Yeah, let's say factor. All right. Long story short is if we have, let's say, a bunch of drops that are, some are, let's say, 35 units, some are 42 units, others are 63 units, others are 84, it's not hard to figure out that the greatest common multiple of this is 7. Okay? So the elementary charge in this weird example is 7 units. He did essentially the same thing with these charge drops, with experimental error and all. So we can then ask a question, if I've got this overall amount of charge, how many electrons does this correspond to? So this is assuming we know what the elementary charge is. So that's pretty simple. We just take the total Q and we divide it by the charge of an elementary. So 1.9 times 10 to the negative 16th divided by 1.6 times 10 to the negative 19th gives us, about 1,200 E's. Okay. So I'm going to stop there. I want you to understand the schematic idea behind the Millikan oil drop experiment. In the lab, we'll do some analysis and analogy with mass to figure out elementary mass by finding this greatest common multiple. Okay.